All right, the notation that you need to associate with binomial probability distributions. Whatever we're studying, that's what we're going to call success, and we're going to use capital S for the event of success and capital F for the event of failure. Um, little p and little q will denote the probabilities of S and F respectively. So little p is the probability of success, little q is the probability of failure. And since there are only two possible outcomes, success and failure, if you give me p, then I can find q. If you tell me the probability of drawing out a pink marble is zero point 0.7, then the probability of not drawing out a pink marble is zero point 0.3. Just subtract the probability of success from 1, and that will give you the probability of failure. Other notation that's very important in order for you to either use the formula for calculating mean of a binomial probability distribution or to calculate it on the calculator, you have to understand what these variables stand for. N is the fixed number of trials. X is a specific number of successes in N trials. I may say, um, what's the probability of 5 out of 13 girls in 13 births? What's the probability of 5 of them being girls? In that case, 13 is the number of trials and 5 is the number of successes. X has to be a whole number. You can't have a partial success, and it has to be between 0 and n. If I have 13 births, then the fewest girls I can have is 0, and the most girls that I can have is 13. So X is always a whole number between 0 and n. P is the probability of success, Q is the probability of failure, and P of X is the probability of getting exactly X successes among N trials. Be sure that X and P both refer to the same category being called a success. If success is drawing a pink marble out of a bag, then P has to be the probability of drawing a pink marble out of the bag. Or if S is, if we're studying again cancer patients and we say that X is the number of patients who have cancer, then P has to be the probability of drawing a patient with cancer. So make sure you clearly associate both X and P with whatever you've called success. And then here again is the guideline for cumbersome calculations. When sampling without replacement, consider the events to be independent if the sample size is less than 5% of the population. So even in events that are technically not independent, as long as our sample size is less than 5% of the population, we can pretend or assume that the events are independent. All right, how about this formula for binomial probability calculations? That is an interesting formula, and just let me mention to you, well, two things. Number one, we're not going to use the formula. I'm going to show you how to find the formula or find this value on the calculator. But also, just in case you're wondering what that exclamation mark is, N with an exclamation mark doesn't mean in a really loud voice. That's called N factorial. And for example, if I had 5 factorial, that would mean to multiply 5 times 4 times 3 times 2 times 1. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. All right. I just wanted to show you that formula so that you would truly appreciate your TI 83 and 84 and what it can do for you. It can find the probability of X successes faster than you can even read that formula. And again, what you'll need to substitute into the calculator, what you'll need to enter is the N, which is number of trials, the X, which is your number of successes, and the P, the probability of success in any one trial. If you give the calculator this p-value, it can calculate the q value that it needs for the formula. So how do we do this on a TI-83 or 84? To find the probability of X successes in N trials where each success has a probability of P. Very important that you understand those variables. X is a number of successes, N is a number of trials, P is the probability of success. Choose second and VAERS. Right above your VAERS button on the calculator, it says DISTR, and that stands for distribution. We're going to talk about several kinds of distributions, but because distribution is in yellow above the VAERS key, to access it, I have to press second and then VAERS. Well, maybe I should turn it on first. Second and VAERS. And then I want to scroll down until I see binomial PDF. Right there it was. On my calculator, it's 0, binomial PDF. Now there's also binomial CDF, and we'll talk about it in a minute, but right now we want binomial PDF. So I'm going to choose that. On the operating system that's on my calculator, when I choose binomial PDF, it immediately goes to a blank screen, opens a parentheses, and waits on me to enter 3 values. The 3 values that I need to enter are the value of N and the value of P and the value of X. On some calculators, rather than going to this blank screen that says binomial PDF, you'll go to a screen that has binomial PDF at the top, and then it asks you for number of trials, number of successes, and probability of success. If that's how your calculator operates, you just enter those 3 numbers. For me, I'll need to enter the N and the P and the X separated by commas. One thing that will help you remember in what order to type in the 3 variables that you have to enter, you enter them in alphabetical order, the N and then the P and then the X, and press enter. Now, let me say this about the homework and specifically the view example and help me solve this tools in MyLabs Plus. From here on out, we're going to be using the calculator for almost everything that we do in statistics. But those help tools in MyMathLab are going to refer to formulas and tables in the back of the book. That will mess you up. Disregard if you use help me solve this or view example in MyLabs Plus, you only need to use it to make sure that you're getting the right values for N, P, and X. You can do that. But once they start plugging those values into this formula, you need to close the window, get out of help me solve this or view example, because we're not ever going to use that formula, and we're not ever going to use, well, one exception to that, and I'll tell you when we get there, but there's only one of those tables in the back of the book that we're going to use. So when MyLabs Plus shows you from the table in the back of the book, just close it. All right, let's see how this works. The brand name of McDonald's has a 95% recognition rate. Now, I don't know if that's in the US or in the world. Certainly, at least in the US, 95% of the people you ask would say, yes, I know what McDonald's is. It may even be the world. I don't know. If a McDonald's executive wants to verify that rate by beginning with a small sample of 15 randomly selected consumers, find the probability that exactly 13 out of 15 consumers recognize the McDonald's name brand. All right, remember what these variables stand for. N is the number of trials, or the sample size in this case. We're talking about 15 people in the sample. I'm sorry, I can't get that to mute. but it will stop ringing in just a second. There's 15 people in the sample. The probability of success, we're told, is 95%. I want to verify that the probability of someone knowing the name brand McDonald's is 0.95, and I want the probability that exactly 13 out of 15 do recognize that name. So X is 13. I'm going to pull up binomial PDF and enter the three variables in that order, n, then p, then x, 15, comma, 0.95, comma, 13. And I get that that probability rounded to 3 decimal places is 0.135. Now think about this a second. That's supposed to be the probability that 13 out of 15 consumers recognize McDonald's name brand. Um, if there's a 95% recognition rate, I would have thought that the probability of 13 out of 15 going, sure, I know what McDonald's is, I would have expected that probability to be much higher. Why is it so low? There's only a less than 14% chance that 13 out of 15 will be the number who recognize McDonald's brand name. The reason that probability is so low is because it's much more likely that either 14 or 15 will recognize the name brand. If there's a 95% recognition rate, then you would expect more than this 13 to go, yes, I know what McDonald's is. What about the second statement here? Find the probability that the number who recognize the brand name is not 13. Well, this is the probability that the number who recognizes the brand is 13. Not 13 is the complement of that. So to find the complement of the probability for 13, you could just say 1 minus 0.135 or 0.865 is the probability that the number who recognize the name brand is not 13. Let me put just a couple of other problems down here at the bottom. What about the probability that 14 out of 15 recognize the name brand McDonald's? To get the probability of 14 out of 15, I would enter binomial PDF out of 15 people, each having a probability of 0.95 for recognizing the name brand of McDonald's. What's the probability that exactly 14 of them do? I pulled up binomial PDF, 15, comma, 0.95, comma, 14, and found that probability to be higher, 0.366. And then I think I have room to squeeze one more example here. What about the probability of 15 out of 15? There's a 95% recognition rate. What's the probability that all 15 people go, yes, I know what McDonald's is? I'd enter that as binomial PDF 15.95, 15. And I got that probability to be 0.463. So there's almost a 50% chance that all 15 people will say, yes, I know what McDonald's is. Or if we add these two probabilities together, we get about a point 0.8, no, point 0.3, 0.83, 83% chance that either 14 or 15 will say, yes, I know what McDonald's is. All right, I need to stop this video. I need to go teach another class, and then we'll call this one part one. I will come back and take part two in a little bit. So you may need a break as well. Go ahead and take it, and we'll pick back up on the next slide, which is cumulative probabilities from binomial distributions.